My research project is about the causes and effects of climate change in the Amazon rainforest. But to understand the specific events occurring in the Amazon, we first need to understand what climate change is in general. So what is climate change? Climate change is a long-term change in average weather patterns of both local and global climates. There are many different aspects that contribute to global climate change, but the first aspect that I focused on was air pollution. Air pollution occurs when too many aerosols or greenhouse gases are in the atmosphere, which leads to an increase in global temperature. An aerosol is a solid or liquid particle in a gas that affects the chemical makeup and temperature of the atmosphere. A greenhouse gas, or GHG, is a gas that absorbs radiation and warms the atmosphere. The difference between the two is that GHGs create a warming effect on the atmosphere and raise the temperature, whereas aerosols actually create a cooling effect. This is a diagram of the net radiative forcing of aerosols and GHGs. The blue curve shows that aerosols have a negative radiative forcing due to their cooling effect. The red curve shows that the GHGs have a positive radiative forcing due to their warming effect. The black curve, representing the total anthropogenic emissions, shows that the addition of aerosols and GHGs creates a total positive radiative forcing, and therefore a warm temperature. This is a graph that predicts what would happen to the global temperature if we kept the masking effect of aerosols versus taking out all cooling aerosols. You can see in graph 2 that without the masking effect, the emissions go up past 2 degrees and hit approximately 2.5 degrees. In the first graph, with the masking effect, the temperature remains lower and has a smaller possibility of crossing 2 degrees. The quantity 2 degrees is extremely significant for determining the future of climate change. Many countries have agreed that the global temperature increase should not exceed 2 degrees Celsius. This number is referred to as the DAI, or Dangerous Anthropogenic Interference Threshold. This means that human action continues to increase temperature, but 2 degrees Celsius is the point at which there is significant damage to the environment. If we go over this limit and the temperature continues to increase, as shown in the diagram, there could be many disastrous effects. As soon as we reach 2 degrees, the amount of danger starts to rapidly increase, and ecosystems begin to approach what are called tipping points. Major irreversible effects on a climate system are called tipping points. A tipping point is defined as a critical threshold where a climate system crosses into a new state, or a point when a series of small changes suddenly creates a significant large change. This map shows multiple tipping elements, which are systems that each have their own tipping point, all across the world. A tipping point usually comes from a major characteristic of a tipping element. In my research, I focus on how breaking the DAI threshold would affect the tipping point of a specific biome, the Amazon rainforest. My hypothesis was a temperature increase of 2 degrees Celsius or more will cause a long-term decrease of both precipitation and biodiversity within the Amazon rainforest. The first factor to be affected by atmospheric temperature that directly involves the Amazon rainforest is sea surface temperature, or SST. The increased global temperature causes an increased SST in the Atlantic Ocean. A warmer SST will create more water vapor over an area, resulting in increased rainfall. Warmer SSTs have been connected to some of the largest recorded floods in the Amazon in 100 years. However, the SST is not the main reason for increased precipitation in the Amazon. When the SST is warmer, it directly affects 2 key weather phenomena in the Amazon, ITZZ and ENSO. Both of these have major connections to the amount of precipitation in the Amazon. ITCZ, or Intertropical Convergence Zone, is a weather phenomenon described as a band of storms across the equator caused by converging trade winds. The boundaries of the ITZZ are the Tropic of Capricorn and the Tropic of Cancer. A warmer SST allows the ITCZ to move between this range, which brings rainfall to a new area. It moves with the sun as the seasons change. However, a warmer SST can cause the ITCZ to move regardless of the season. When the Atlantic Ocean has a warmer than usual SST, the ITCZ will move southward and increase precipitation over the Amazon. This is an example of how the ITZZ moves southward of its climatological position during 3 different flood years. ENSO, or El Nino Southern Oscillation, is a cyclical recurring weather phenomenon in the Pacific Ocean, where the fluctuation of SST in atmospheric pressure affects the surrounding environment. There are three phases of ENSO: El Nino, neutral, and La Nina. El Nino is the phase of ENSO that creates excess warming in SST, precipitation, drought, and storms across different areas of the world. In South America and the Amazon rainforest, it usually creates extreme droughts. La Nina does the opposite. It creates excess cooling. The warm SSTs show that there is an increase of precipitation with the Amazon wet season. This also causes the dry season to become longer and more intense. The Amazonian dry seasons usually last less than 4 months, but according to recent data, it has begun to grow longer. Warming of the SST in a certain area will increase the dry season of others. Climate change is starting to make El Nino events stronger, and this leads to predictions that the Amazon will continue to dry out. But as the Amazon dries out, what will it turn into? The best guess that we have is that it will turn into a seasonal forest. The Amazon currently has 25% of global diversity, about 2,000 to 3,000 millimeters per year of precipitation, and a mean annual temperature of 26 degrees Celsius. 3 Amazon tipping points are passing a temperature increase of 4 degrees Celsius, having 40% of deforestation, which would be primarily man-made, or precipitation that decreases by 30%. As rainfall decreases in the Amazon, the risk of fire during droughts increases, which will cause further deforestation. This in turn will force species to either adapt to a new biome or to migrate somewhere else, decreasing species richness while increasing occupancy turnover. This diagram shows the average precipitation of the rainforest, seasonal forest, and the savanna. Unlike the Amazon, a seasonal forest has an average precipitation of about 750 to 1,500 millimeters per year, whereas the savanna has about 500 to 1,000 millimeters per year. Though the data that I compiled through my research cannot determine for certain the future of the Amazon rainforest, it is clear that there is a connection between the changing climate of the rainforest and global temperature. And these are all of my references. And that's the end of my presentation.
Okay, I have a couple questions for you. My first one is, so you're talking about like tipping points and stuff. So I was wondering, is there like a point where adding more aerosols to the air would stop counteracting the warming effect of the greenhouse gases? Or like, should we be adding more aerosols to the air to help counteract the warming? Or would the effect of the pollution from them be like worse than the warming effect caused without them?
Mm-hmm. So there's actually a geoengineering proposal to artificially inject more aerosols into the air because it can imitate the results of volcanic eruptions. And volcanoes actually release a lot of aerosols into the atmosphere, which creates a decrease in global temperature. And this process would reflect sunlight from the earth, which creates a more long-term cooling effect. And this is viewed by a lot of people as a good temporary solution to global warming, because it would be pretty easy to reverse if something went wrong. But there's also some research that supports the idea that it wouldn't work well because it can cause lots of health effects in humans, and it can affect weather and cause extreme droughts, temperature fluctuations, storms, or floods, and it can also deplete the ozone layer. So I can't say whether or not it would work better to put aerosols into the atmosphere. It really depends on what sort of benefits you're looking at, but it is a proposed solution, so it's possible.
Okay, yeah, that makes sense. I have one more question. So you were talking about like the tipping points, and so how do you determine that an event would be a tipping point? Is there like a way to predict that or determine what the tipping point would be before you observe it or before it's like been reached, or is it kind of observational in that way?
Well, there's actually like a really long mathematical equation to determine a tipping point, but if you're just looking at it from like an observation standpoint, it really just depends on like their own individual parameters, like temperature, precipitation. Like for example, the ice sheet in the Atlantic, that depends on how much ice it's still retaining. So when it surpasses like a certain critical value, like losing a certain amount of ice, then that tipping element would reach its tipping point. And then there's some tipping elements that don't have identifiable tipping points. You would probably have to use that equation. So it really depends on what the element is and like what its parameters are.
Okay, thank you.
Welcome.